So we're going to look at how the internet and how the internet infrastructure actually works. And to do that, I want to talk about three particular things. I'm going to talk about TCP/IP, the domain name system, and then we're going to have a look a little bit deeper into HTTP web servers and web browsers. With the web, we know that the way that this works is that there's a user on a machine somewhere and there's a server in the background. And more specifically then, you've got web browser software and web server software running in the background. When the user types in an address like google.com, that's a URL, that stands for Uniform Resource Locator. What actually happens is that is sent over the internet using HTTP, Hypertext Transfer Protocol, to a web server somewhere on the internet. The web server finds the page, and it's a very simple piece of software, a web server to an extent, because all it really is listening, waiting for some request for a page. When that request comes in, it finds the page and it sends it back, and then the browser displays a page. So to actually publish a web page, what we need to know is where the server is on the internet. This notion we're actually going to connect to publish a web page, to actually gain access to a page. We need access to a particular machine somewhere which has an internet presence. So what that really means is that web servers have to have some space on the internet somewhere. And it's not just a matter of having space, it's also a matter of having a way for us to actually contact that machine, having an address for that machine. And that, of course, does entail having sort of addresses that we can understand. And those three things together make that work. TCP/IP, the DNS system, and HTTP all work together to enable the World Wide Web to run over the internet. So let's have a look at TCP/IP. Now, this is going to be an abstract explanation of TCP/IP. If this was a sort of data communications and networking course, you could spend weeks on this subject, and it's a really very detailed, complicated subject. So I'm just going to take a very abstract, high-level view of TCP/IP to sort of paint out some of the broad aspects of it. Well, TCP/IP sort of gives us two things. It gives us an addressing mechanism, and it gives us a way for a message to be transmitted to a particular address. Now, that addressing mechanism is called an IP address. And what TCP/IP enables us to actually do is to transmit a message to a particular IP address. So it's very similar to that notion of post, if you like. You can imagine an envelope with an address on it. We're sending that, we're transmitting that to a particular address. Now, TCP/IP originally was funded out of the American Defense Department. What they were primarily concerned about, and this was some years ago, was this notion that they could develop a robust network that would survive military attack. And this grew out of work from research groups, universities, and eventually they come up with this kind of standard networking protocol, which, as it turns out, has formed the backbone of the internet. Now, there is a consequence of this notion that the network infrastructure should be robust, and I'll talk about that later on. So, IP numbers then, well, every machine has to have a unique number, and that unique number is its unique address. And no other computer, no other device connected to the internet should have that number. We want every address to be unique. And you can hold that idea in your head for the moment. It's not actually true in practice because of lots of other reasons. But for the moment, just imagine every IP address is unique. So if everyone has a unique IP address, and that's in your phone, in your computer, in your laptop, in your gaming console if it's connected to the internet, that unique code gives us a unique way to contact that device. It's a 32-bit code, and it looks something like that. So 32 ones and zeros. Often it's written down using a special notation, it's called dotted quad notation. And what happens is each 8-bit pattern is written down as a base 10 number. So for example, that pattern there, you could go through and you could convert that and it would be 149.76.12.4. That's a very common pattern that you'll see all the time. What we're really talking about here is that's an IP number, that's an address of a machine. So how does transmission actually occur from you to a particular address, for example, to that particular number? And again, I'm going to take a very abstract description of this here. You can take the message, whatever the message is, so you could sort of visualize it as if it was an email or a web page that you're actually trying to retrieve. You take that message and you divide it into smaller packets. So you sort of cut it up into chunks. You label each one with an address, and then you send it out over the internet. And those packets are sort of sent across the internet, and when they get to the destination, they're reassembled in some way. Now, there's no guarantee that packets travel the same route, but the truth is, generally they do. But the advantage of this system is that, of course, if some of the nodes go down, it should still be possible for packets to find their way from the start to the destination. And there are all sorts of checks and mathematical processes built in to the TCP/IP to ensure that if packets don't arrive, we can ask them to be sent again. If there's a slight corruption in a packet, we might be able to recover the contents of the packet just from sort of error codes and mathematics that are built in. So there's lots and lots of error checking and redundancy built into the system to ensure that packets arrive eventually, somehow. And that's where this notion of robustness comes from. Broken nodes don't stop the transmission. Now, the consequence of that robustness means that we can't guarantee time for transmission. We sort of go, well, we don't know what route this is going to take, but we can guarantee that the packet will arrive eventually. And the consequence of that is that some real-time applications which attempt to work over the internet are going to have problems. And a classic example of this is YouTube. YouTube uses really sophisticated buffering to enable it to transmit 24, 25 frames a second over the internet. What it tends to do is it uses mathematical models to actually change the bandwidth of the image, or it might download as much as it can before it starts playing the image. All sorts of techniques have to be used to ensure that we can get sort of real-time video transmission over the internet. And that is a consequence of when we are trying to do real-time applications, even things like gaming, for example. Now, originally, there was one organisation sort of administering all the IP addresses, the IANA, the Internet Assigned Numbers Authority. And obviously the internet was an American controlled and funded organisation. But over time, their impact has lessened. They're, if you like, still at the top of the tree. There are lots of other organisations and companies and commercial organisations controlling, distributing IP addresses. Users or companies would never interact with them. Typically, what you would do is you would interact with a local organisational body or with a local company. So, for example, universities in the United Kingdom work through an organisation called Janet. Companies, let's imagine you're a small or medium-sized organisation, you might contact an internet service provider like BT or someone like that, and you have a commercial contract with them to supply you with IP numbers and an internet connection. Numbers are classified into groups, and I don't want to go into this into too much detail, but there is an important set of numbers here, the Class C numbers. And the reason that these are important is because these are special numbers that work on local area networks, but are not actually transmitted over the wider internet. Now that sounds a bit weird, but I will come back to why those numbers are important at a later point. So you will have been given, when you connect to the internet on your home machine using your Virgin cable connection or BT or whatever it is that you're using, you're gaining access, you get an IP number, and you're using that IP number. That's your computer's IP number, your connection to the internet. Now I'm glossing over lots and lots of details here to do with port numbers and routing and subnets, but I just want to give you a feel for the higher order concept of how important it is to have an IP number, and you use the IP number. Let's have a look at an example of that then. And peer-to-peer networks are one of the most recent innovations over the internet, really. The way that peer-to-peer networks work is that we have a whole bunch of people and they're sharing their music, and you have a central database which is containing information about who's sharing which music. And one of the most common peer-to-peer networks currently is BitTorrent. So you have all these BitTorrent clients and you have a BitTorrent server. And the way that it works is, let's imagine Tom is searching for some music, and the central server, Tom connects to the central server, and that's a database of who is sharing which files. And the central server reports that these two other people are sharing that music. And then what happens is the file is downloaded from both machines. Now this example just uses 2 machines. It could be 1,000 machines, it could be 20,000 machines. That's how peer-to-peer networks work. So how does that actually work if you think about it in terms of IP numbers? Well, you might think that IP numbers mean that you're anonymous, but you're not, because of course there has to be that central list of shares. So what's actually going on here is each machine has got an IP number. So as you can imagine, each of these machines has got an IP number, and that central list of shares is maintaining a list of IP numbers and who is sharing which file. So that's why you have to be very careful about using BitTorrent, because of course you mustn't illegally download music or files or anything like that. You will be publicly visible. Your IP number will be visible, and somewhere there will be a database saying which files you are sharing from your IP number. So how do you actually get an IP number? And I've indicated that basically you're going to get it through a local organisation. If you're a business, well, you could basically go, well, I've got, 40 machines, I need 40 IP numbers. And then you could actually visit each machine and you could put the IP number inside each machine. That would be called a fixed IP address scheme. And that's something that we used to do sort of in the 70s. We don't do it like that anymore because it's not very efficient. But that's the notion. The notion is, I've got 40 machines or 100 machines or 30,000 machines. I'm going to need some way of actually allocating an individual unique IP number to each of these machines. Sometimes you have to have a machine that's got a fixed IP number because it's always got to be discoverable, and that would be things like web servers, mail servers and stuff like that. But the disadvantage of it is it's not very cost effective. It doesn't really match the kind of working practices that we have now with mobile working, mobile phones, laptops, all these different devices that are being connected to the internet and then disconnected. So in reality, what most organisations do, and in fact this is the same way that internet numbers are probably allocated in your home, is that some of those IP numbers, and I did reference them earlier on, some of those IP numbers are specifically for local area network use only. So those numbers are not forwarded over the internet. Now what that means is that you can just purchase a small number of real IP addresses, and those are shared amongst all the different machines on your local area network. You'd have something like this. So inside your local area network, you've got hundreds of thousands of machines, and they are using some of those special numbers that are in that category C, numbers beginning with, like, for example, 192. And you only have a limited number of actual IP numbers, real IP numbers, and those IP numbers are shared using some sort of translation piece of software. And that's exactly the setup that you've probably got at home. You've probably got some kind of modem and router. You'll have one real IP number. And what the modem router is actually doing is it's using some of those made up IP numbers from, for example, that 192 category. And those are the numbers that are actually allocated to the devices on your home Wi-Fi, on your home network if you're using cables. So it would look something like that. Now, most organisations don't want to actually have to go around to every single device typing IP numbers in. That's obviously not practical if you've actually got tens of thousands of machines. And you didn't do that when you're at home either. So what most modem routers do and what most organisations do is they run a piece of software called a DHCP server. And what that does is it's like a library of IP numbers that are going to be temporarily loaned to people. And that's called leasing an IP number. So if somebody connects to your home network, what happens is when they connect, they log in, they're actually getting one of those temporary IP numbers which allows them to gain access to your home network. So for example, at the university, every device which is hardwired into the university network has a MAC address, and what MAC addresses are is a unique number that exists on every network card. So when you try to connect a machine to the university network, that MAC address is checked to see if it's an authentic machine, and if it is, it then gets a proper IP number. Something similar then happens. Let's imagine you're using Wi-Fi at the university. You'll connect to the Wi-Fi system and it will give you a sort of temporary IP number, and what you'll have to do at that point is you'll actually have to log in, and when you log in you get a proper IP number that's allocated to your phone or your laptop, whatever device you're using, and that's what you use to actually connect to the internet. Now, when the TCP/IP numbering scheme was originally created, there was no idea that we would be connecting so many devices to the system. No one had this vision that you would have mobile phones that needed IP numbers. You'd be running gaming consoles, TVs, computers, laptops. So a few years ago, it was realised that we were actually kind of literally running out of numbers to be allocated. And so IP version 6 was proposed. Over the last few years, we've been moving towards IP version 6. And IP6 basically uses 128 bits rather than 32 bits. So obviously you have a much wider range of numbers that you can use for addresses. It turns out that using all those schemes that I've sort of mentioned in passing, some of those category C numbers, all sorts of other techniques, means that that crisis point wasn't quite as problematic as we thought it was going to be, but we're still moving towards IP6. So that notion that we will have, we can give everybody on the planet so many numbers, there won't be a problem.